up is Kristine Olsson, and Kristine has been with the Johnson County Sheriff's Office Crime Lab for nearly 5 years. She's been in forensic science for 14 years and is happy to say that doing away with trace evidence section, the Johnson County Sheriff's Office Lab enjoys the distinction of reestablishing this discipline. And she is going to be talking to us today about a proposed standard test method for forensic analysis of glass using capillary micro X-ray fluorescence spectrometry.
Thank you. I originally submitted this as a poster presentation, so I alternate between thanking the organizers and cursing them for putting me up here. But no, I'm very pleased to be here. My work today is presented on behalf of the Elemental Analysis Working Group. There's a number of posters and presentations by this group throughout the week, and basically this presentation concerns a proposed standard method for XRF analysis of glass samples. I'll be speaking with you today about basically the history driving the proposed standardized method. Why did we feel that there was one that needed to be put out? Also, we'll discuss some of the aspects of the analytical recommendations that we make in the method, some of the instrument parameters, and some of the recommended QC measures that are in the method, as well as a sample analysis scheme, an evaluation of the results, which includes basically how you look at your spectra, or how do you evaluate your spectra, and interpretation of results, which is inclusive of recommended match criteria. We'll finish up with a timeline for completion of the method and review and submission to ASTM for acceptance, hopefully. A little bit of background on the Elemental Analysis Working Group. It was established by the International Forensic Research Institute at Florida International University under a grant from NIJ. The aims of the working group were two-pronged: to improve the forensic analysis of glass through validation and standardization efforts and examining the way the different instruments performed, from LIBS to XRF to the ICP-MS systems. And also the other prong was to develop standardized methods, incorporating recommended match criteria. So you've already heard how some of the match criteria performed for Emily's work, and there is a presentation coming up also which discusses the way match criteria performed among all the different instruments. So why a standardized method for XRF? In the 2010 CTS reports, approximately 69% of the labs are using some sort of elemental analysis to render their conclusions for glass. Standard methods do currently exist. There's an ASTM standard for solution-based ICP-MS. However, micro-XRF is the preferred method for most of the labs in the US. Approximately 35 to 40 of the labs are currently using micro-XRF. And right now there is no standard published method for addressing the use of XRF for analysis and discrimination. When we brought on glass in our laboratory, we tried to find out what other people were doing as far as their match criteria, and pretty much the answer was all the same, is that you need to talk to Scott Ryland. Just go talk to Scott Ryland. So Scott Ryland we're trying to standardize Scott, basically, and get him on the books before he retires for good and leaves us. The method that we've put together addresses only source discrimination, so K versus Q comparisons. And it discusses the use of mono and polycapillary optics and energy dispersive X-ray detectors. The method does not address the end-use classification of glass, which we did talk about, but didn't end up going that route. And you can use XRF to determine whether a glass is from a window or whether it's from a container, but not in this particular method. How many of you are XRF users out here? Okay, quite a few. For those of you who aren't, just a brief background on XRF. It is a completely non-destructive method, and it's based on the emission of characteristic X-rays following excitation of the sample by the X-ray source. So you have your source here, it strikes the sample, and emits characteristic X-rays that are then detected and separated by energy in the detector. It works mostly for elements that are atomic number 11 or greater, so basically for all practical purposes, sodium and up. The method that we've put together is all based on data that was collected through the Elemental Analysis Working Group, and it's based off the 4 round-robin studies that were done. Each of those 4 round-robins had a KQ comparison aspect to them, and they range from December 2008 to August of last year. And they range from being very simple, so 1K compared to 1Q, up to very challenging tests of multiple Ks, multiple Qs from glasses that were all produced in the same plant at very close time intervals. One of the recommendations that did come out of the working group and the round robins that we performed is recommending the use of the reference sample, something like 1831, included in every run that you do with your glass. So it's run, every time you run your glass analysis, you include 1831 as a sample and run it under the same parameters that you run your samples under. And this can be used for various things. It can be used to normalize your elemental ratios, which we'll discuss in a minute. It can be used to normalize for interlaboratory comparisons. So you can compare your data with data developed from a different lab. And it normalizes basically instrument response between different laboratories. It can also be used for interlaboratory data collected from different days. So if you run your samples on different days, you can still compare them back to each other using 1831 to normalize. And finally, it's a QC check to monitor performance of your analytical method. This is a spectrum of sheet glass, basically. This is 1831. And when we talk about elemental ratios, for those of you who don't do XRF currently, it's referring to making a ratio of the relative intensity of your calcium peak against other elements in your sample. So for example, you could ratio the intensity of calcium to the intensity of iron and use that as a semi-quantitative comparison for your sample. Although you can do quantitative data with XRF, for glass analysis, because of some of the limitations, we do comparison on a semi-quantitative basis. This is my data. So right here, these are my instrument parameters for my particular lab. Every lab doing the round-robin studies came to the table with their own parameters. And then over time, we kind of optimized parameters that work best from what we were seeing in the studies. And this is some of those instrument parameters included in a sample analysis scheme. These are some of the recommendations that we make. A spot size range is needed for glass analysis between 10 micrometers to 2 millimeters. An excitation voltage for your instrument of at least 35 kilovolts to excite your higher end, higher energy elements. A beam current not to exceed 50% dead time. A mid-range time constant, which gives you the best compromise between counting statistics and resolution. A lifetime providing reasonable counting statistics, for example, in a monocapillary system with 100 micrometer spot size, 1,200 life seconds will give you good counting statistics for a good spectrum for comparison. And then these two aspects here, presentation of a flat surface of your glass sample to the X-ray beam, which will minimize your takeoff angle effects. On full thickness glass fragments, that's really not a problem since generally they have two flat surfaces and they're nice full thickness. On small fragments, that gets to be a little bit more difficult. And when evaluating K and Q against each other, it's very critical to use fragments of similar size and thickness to minimize your critical depth effects. And basically, when we did our round robins, we were requested to run exactly the same number of replicates on all of our samples. So these parameters were standardized, and they performed very well among all the different laboratories. So the recommendation is that on your question fragment, a minimum of 3 replicate measurements should be taken. And when you're characterizing your known standard, a minimum of 3 replicate measurements on 3 different fragments from your known should be run for a total of 9 replicates. When evaluating your results or evaluating the spectra that you've obtained, these are the recommendations that we make. The first is the overall assessment of your spectra. So assessing your spectra to determine if what elements you have present and discriminating your artifact peaks from your 2 element peaks. The recommendation is that in order to determine whether an element is present, there should be a signal-to-noise ratio of 3 or greater, and that element may be identified. Troy Ernst, who is also in the working group, is going to be speaking after the break about when is a peak. So when do you actually call a peak in your XRF spectra? The next step is to do a spectral overlay when you're doing your KQN comparison. So you overlay your spectra one on top of the other. For some laboratories, including some that participated in the working group, this is their only basis for comparison. They don't do any other statistical calculations. It's simply a spectral overlay. And when you overlay your spectra, you want to ensure or verify that the same elements are present in the same relative intensities of your spectra. And the last evaluation is the semi-quantitative evaluation, where you calculate the ratios and determine statistically if they are different or significantly different or the same. You want to, when you're calculating your ratios, you want to use elements, and this is recommended to use elements that are close in atomic number or close in energies. Those will suffer the same takeoff angles similar to each other. And in order to use an element in a quantitative ratio or semi-quantitative ratio, it needs to have a signal-to-noise ratio of 10 or above. And again, Troy will be addressing the applications of these two recommendations specifically to XRF data in his talk. For match criteria, it's recommended, or you may use either of a range overlap or the calculation of 3 standard deviations of your calculated elemental ratios as your statistical measure. So what we have basically is, again, this is a spectra of sheet glass. It's 1831. And just looking at that first step, the evaluation of your spectra, and determining whether you have artifact peaks, like the copper. This isn't really copper in your sample, but it is an artifact peak. And this is a pileup peak of some of the other things that are present in your sample. These are common elements that are seen in glasses. There certainly can be other elements included in there, not just these. And you also want to check your spectra for artifact peaks, such as escape peaks or some peaks. Once that's been established, then you move on to a spectral overlay of your K and your Q directly on top of each other. Just looking at this, we'll be looking at asking you to focus on the iron and the manganese in here. This is from round robin 4 that we did in the working group. And this is a KQ comparison. Your K is blue, your Q is red. And for the XRF users and even for the non-users, if you were looking at this and assessing it, would you say that those glasses, by a show of hands, are different? See some people putting hands up. How about now when you can see the peaks a little bit better? There is a difference here in the iron peak, the intensities that you see here. So the difference is a little bit notable. These are different glasses. They were produced in the same plant, approximately 1 month from each other. At this point, if you were doing a spectral overlay and assessing this, at this point you could discriminate those samples and stop there and say that they are different. Or you could go on and calculate your statistical calculations to determine if they are different or not, or basically prove that they're different. Looking down here at the manganese peak, down here, it's kind of down here in the weeds and it looks a little bit messy. The question comes into play, is that a peak or not? And these are the kind of samples that actually inspired a little bit Troy's talk and his work, so you don't want to miss when is a peak. But this down here, if you apply what he's going to be talking about to that, you can do a calculation that determines that yes, in your Q, you can call that present as manganese as being present, but not in your K. If you'll notice, the calculation is not 10 or above, so you can't use it in your semi-quantitative comparison, but it is distinctive that it's there in one and on the other. That was the first Q. This is the same K compared to a second Q. And looking at this, by a show of hands, would you say this is different? These glasses are different? Nobody? Gosh, you guys are so good. These glasses are indeed the same. They are from the same source. But if you do notice here, there is a little bit of a difference in the intensity of your peak. And at this point, this is the kind of situation where you could go on and do your statistical calculations to show that they are significantly different. These ratios here are recommended ratios in the method. And again, if you have something else in your sample, you're not beholden to just use these. If there's another element that is applicable in your sample, you could certainly incorporate those calculations for your comparison. And also by that same token, if there's something in these ratios that is missing from your sample, then you're not beholden to include that ratio. For the interpretation of results or the match criteria, again, the recommendation is that you can do one of two things. The elemental ratio range overlap. So you would characterize your known and get the complete range of ratio calculations in your known. Do the same thing for your Q and determine whether those ratios overlap. In some of our labs that participated, this is their preferred method of statistical evaluation. And it has two benefits in that it's non-parametric, it's very easy to explain to a jury. The other thing is you could do 3 standard deviations. So from your K, you determine the mean, determine your 3 standard deviations, and that becomes your range to compare to. Then you determine the average of the calculated ratios in your Q and see if that average falls into the range created by your known. In doing the round robins, these two statistical applications performed very, very well, comparable to each other. And this is applying it to the 2 samples that we've already looked, the Ks and Qs that we've already looked at. So in blue, you have K1, the calculated calcium to iron ratio, the mean, the standard deviation, the created range. The Q1, the calculated calcium to iron ratio, is 2.98, which does fall in. So they are the same source, K and Q, and there's a nice overlap in your spectra as far as range overlap goes. This is range overlap calculated for the K that we looked at. The Q1, which did not match and does fall, when you do your calculated range overlap, the ranges do not overlap, so this statistically is found to be different. And then the K2, which is from the same source, all the ranges do overlap with your K. For the 3 standard deviations, it performs the same way. So here's the range for your K glass, the Q1, which did not match, the calculation, the mean of all of your replicate measurements on your Q, the calculation for that is 1.98, which falls outside of this range. So they are found to be significant, there's a significant difference between that Q and that K. For K2, which was from the same source, the calculated average does fall into the K1 range. And again, these glasses were K1 and Q2 were produced in the same plant at the same time, or I'm sorry, those are from the same source. K1 and Q1 were produced in the same plant a month apart from each other. What the method does not address is a significance of the elemental association. The only thing we do as far as is go to match criteria and interpretation that way. There's no addressing of significance. There's also no discussion of a consensus for language describing that significance, and all that is still under discussion in our working group and I know in other circles. And again, this method does not address the use of XRF to determine end-use classification for your question particles. The timeline from here on out is that hopefully the draft will be distributed to SWGMAT following this symposium. SWGMAT will distribute the draft to all their members for comment, and hopefully within 1 month, following review, we'll get those comments back and incorporate those into the draft. Then it will be submitted to ASTM in October for the 4th quarter 2011 vote. And if you are interested in getting copies of the method to review and comment on, Dr. Almiral is available to provide those copies for you, and he'll be speaking later on too as well. These are all the XRF participants that participated. There were 9 labs total that participated in the round robins. You can see right there Scott Ryland participated, so I'd like to thank him for he drove a lot of the work done on this. And thank you to these solution ICP-MS users, the laser ablation ICP-MS, and LIBS users that participated as well. Thank you.
So we will entertain questions for any of our 3 speakers now, if anybody has a question. Yes, sir.
It's not clear to me why you're assuming the 2 unique glass panes, which is what is making the windshield, why you're assuming that they should be the same.
We're assuming that they would be produced in the same manufacturing plant around the same time to make the windshield pane. You'd assume that they would come off the sheet around the same time.
And I agree that in most cases that's a correct assumption, but there could be an instance where the one pane could come off a pallet, that pallet's now empty, they bring in another pallet and bring off the next pane to laminate, and they could have come from conceivably weeks apart in the glass plant. So I agree your assumption will be valid for most cases.
Yes, and that might be true for why not all 11 pairs were associated for this particular site.
Anyone else? Yes, sir.
I have a question for Stefan. You use the same energy density between the two laser wavelengths? That's another question. Have you tried to anneal the glass fragment after replication?
Actually, we haven't, but this is one of the things we will still do, because in the course of thinking about what does a red curve really means, it's not really, printed in the user manual of Foster and Freeman Grim 3, what is a red curve and what does it mean, and in a way, so I digged a little deeper, and after some time I got a pretty good communication to Foster and Freeman, and they said, okay, a red curve means that you really have a problem there, or not you, but the instrument, of course, with contrast and the variation of the contrast, and red curves, curves occur also when the glass has been close to radiation, also radioactive radiation, and this can be overcome by annealing. So certainly we will go into this point and select a couple of glasses and do the annealing. Certainly not for all glasses, but for some of them, yes. Of course, then we have to live that we can't produce fresh edges. We just have to get the embedded material, have to, clean it, do the annealing, and fragments are really tiny now, so it'll be a pain. But I'm certainly, Caroline will give it a try. Yeah.
Yes, sir.
For Kristine, this may be a silly question, but for the labs that do spectral overlay, is it done visually,
Yes.
not numerically?
No.
Ma'am?
Question for Emily. You said that you use silicon as your internal standard. Were you concerned about silicon coming off of, say, the torch and reducing extra error into your method?
No, because it's present in such a large concentration in glass that any sort of other variation wouldn't contribute so much to the peak intensity, most likely.
Any other questions? Going once, going twice? Okay, everybody, you're a few minutes early for your break. So if you'd like to go ahead and take your break now, we'll come back here and we'll start again at 4:30.